I have a small bit of bad news, for maybe not for you, but for the ones who were not here last week, is that there is going to be no video for last week because there was a technical problem. Somehow the webcam, the camera was not running, so nothing was recorded. Okay, so unfortunately, so I will give a little bit of refresh this time to help those who were not present. Okay, so we'll finish first bargaining, and I'll explain when you bargain in a network, there's a theory that let you compute how people will actually figure out to split the money. This is called the theory of balanced outcomes. So this I will explain. And then the next topic is the World Wide Web, something that everybody knows, but you are going to know it better than most people. I'll give some history, the bow tie structure, which actually I already mentioned in the first lecture, Web 2.0, and there's also, which is mostly used today, also how link analysis search is done, and then the famous PageRank algorithm, which maybe you know, but I will present for you, and how modern search works. Okay? So this will use a lot of graph theory. But first, I again want to ask a moment of attention for the war that is still going on in Ukraine and that is still being fought for the freedom and our freedom. Okay. So let me go to. So briefly, we're negotiating. So there's a model, there's a network. This is a simple one with 5 edges. Each person knows a few other people and you negotiate. This happens a lot. For example, buying a house. So if I'm buying a house, so here's a house, here's another house with a seller, and I am looking at this house, but this person, there's another person looking at this house and another house. So this makes a network, you see? Okay, so, and then there's the power. So this seller has only one buyer, but this seller has 2 possible buyers. So there's a difference in power. So this kind of situation happens a lot. If you are in a negotiation situation, it's very important to understand who are the other participants and what kind of a network they have. This is a simple example where you have 5 people, B knows 3, and A, C, D, and E know less. E, C, and A only know 1 person, and D knows 2. We define a simple formal model. On each edge there is $1, or €1, or it could be 1 million euros. It might be a house, for example. And in each phase, this money is split between the 2 endpoints if they agree. If D agrees to receive 80 cents and E 20 cents. And so this will form a matching on the graph, but not a perfect matching because some nodes are left out. Okay, so you remember that model from last week. So this was experimented on, which I will not repeat. But I want to explain now a general framework. How do you negotiate on this kind of network in general? How do you theoretically analyze it? We're going to present a formal mathematical framework that is, in fact, it seems to be the way that humans, the way that rational beings negotiate in real life. This framework is based on 3 principles: the Nash bargaining solution, the ultimatum game, and stable outcomes. And the framework is called the theory of balanced outcomes. So with this theory, if I give you a network, you can determine exactly how in the real world humans will, if they are negotiating and try to get the best result and everything, how they will do, okay? And balanced outcome means that all agreements, so the matchings are Nash bargaining solutions, which I'll explain in a minute. There's also all outcomes that are stable. That means no node can steal another node during the negotiation. And finally, there are no extremes. Human beings do not like extremes. There will always be more, less extreme divisions, okay? This approximates the result of human negotiation as far as we know. There's no proof. This is actually one of the most recent mathematical theories on this. There's no proof. Maybe we need to go to psychology. So I will first explain the three principles, and then I'll show you the theory of balanced outcomes. So some of this was given last week, but I will refresh a little bit more than I intended to, because for an unfortunate reason, there was no video taken last week, okay? So the Nash bargaining solution is a local thing. So I'm looking at two nodes who are negotiating. There's $1 here, and A and B negotiate. How do they split the dollar? So this approach assumes that A has another option, okay? These nodes A and B usually have other possibilities. So A has an outside option of X dollars, and B has an outside option of Y. Okay? So A will only take B if A can get more than X. That's logical. Otherwise, A will take X. And B will only take A if B can have more than Y. Okay? We will assume X plus Y is less than or equal to 1. Otherwise, you can think a little and you will see there's no way they're going to agree. Okay? So A asks for at least X, and B at least Y. How do you split? So the Nash bargaining solution assumes that there's an equilibrium where each one is going to do something corresponding to what the other one does. So how they will do it? Well, A will ask for at least X, B will ask for at least Y. So in fact, if you look at X plus Y, which is less than 1, there's an extra amount, 1 minus X minus Y. This is the extra that they could get if they agree with each other, okay, compared to the outside. So this negotiation is splitting the surplus. But in the Nash solution, each node looks at what the other node is doing. So A will only take part of the surplus if B agrees also. So clearly A will not agree for less than half. Why should A need less than half? Neither will B. But A knows that B will do like that, and B knows also how A will do it. So they will essentially force each other to be fair. So the idea is that the surplus is split in half. A gets X plus S over 2, and B gets Y S plus S over 2. So if you work it out, A will be X plus 1 minus Y over 2, and B will be Y plus 1 minus X over 2. And this is a kind of equilibrium. This is giving the best reasonable result for each of them. And this is called the Nash bargaining solution. Okay, so this is the first principle. The second principle, which I also explained, but I'll go over again. This is the ultimatum game. This is an example of how humans don't like extremes. So assume A and B are negotiating, and there's an extreme power imbalance. A has all the power, and B has nothing. Well, B has only the ability to agree or not. A has $1, or A has $1 million, let's say, to make it more intuitive. 1 million. And A proposes a division with B. A proposes to B, I will give you part of it. And B can either accept or reject. And if B accepts, they both get it. If B rejects, both get 0. So game theory says B should accept any amount greater than 0, even 10 cents out of €1,000,000. Even very small, because it's better than nothing. But humans are not like that, okay? This is something where the human behavior goes beyond game theory. In human subjects, B, if you don't give B a reasonable amount, B will feel very, very insulted. And B will not accept, okay? B will take the loss, accept the loss because there will be a moral victory, okay? So if A offers 1 cent out of €1,000,000, B is going to say, no way, go away. And A gets nothing. And so B is very, very satisfied. So this means that there's something kind of an emotional payoff. B gets a benefit, greater benefit in rejecting a low offer and feeling good. B expects to be treated fairly, okay? So what does that mean in practice? Well, B knows that A has the money and not B. So in practice, B will accept to get less than A, but not so much less. In practice, actually, it turns out to be 2/3 versus 1/3. Okay? So the result is that humans will not agree on extreme imbalances, extreme divisions. They will always bring it back to a more fair division. Okay? For human beings, because of the way, the global way that humans are thinking. Okay, so that's the ultimatum game. And the third one is called stable outcomes. This is the ability to steal negotiation. So you see, you have the Nash bargaining solution, but that's a local thing. But there's another effect, which is stealing. Okay? So to define this, I have to define something with the thing which is called an outcome. An outcome is the result of the negotiation, which is the matching and the number that each node gets. So if you have 3 nodes, for example, A, B, C, then a matching could be AB with 20 cents here and 80 cents here, and there will be 0 here. So this, the matching plus the amounts, is called an outcome. Okay? So I will call it an outcome. We have been talking about it the whole time, but now I want to make it clear. An outcome should be stable. Stable means that no node X can propose an offer to Y such that both X and Y are better than they actually are. So X can steal Y. And an example of that, so here's some examples of outcomes. Some of them are stable, some of them are not. The one at the top left, A, B, C. A gets a half, B gets a half, and C gets nothing. That's not stable. Why it's not stable? Because C can propose 3 quarters to B and 1 quarter for itself, and that will be better than what B is already getting. So C can steal the negotiation, steal the agreement before it finishes. Okay? But the one on the right here, this is stable. There's no way C can make a better offer to B. B is already getting 1. Okay? So C cannot do anything better. The other ones, I leave as an exercise for you. Figure out which ones are stable, which ones are unstable. So here we compare the 2 I just mentioned. In the left one, C can offer 2/3 to B. That's more than what B is getting. And keep 1/3 for himself. They're both better. So why should B agree with A if it's better with C? So that's unstable. Whereas on the right, C can do nothing to improve B's result. Okay? And we can give a formal definition of this. An instability, given an outcome, a matching in a set of values, an instability is an edge which is not in the matching, like BC, joining nodes x and y such that the sum of the two is less than 1, strictly less. And if that's the case, then x can steal. X can propose an improvement. Okay, if it's strictly less, there's a little surplus here which can be given to x and y. Okay, so that's unstable. Now, of course, you can't allow negotiation with instability. In real life, humans will take advantage of that. Okay? So, for an outcome not to have this opportunity for stealing x and y to disrupt, it has to be stable. An outcome is stable if it contains no instabilities. There's no way to steal things. In a human experiment, you expect it. If A, B, and C are negotiating, C, of course, will try to steal. Stability captures something nice in these experiments. It captures the extreme power imbalances. The 0, 1, 0. Why does B get 1 and not less than 1? Well, because of stability. Of course, the ultimatum game says it'll be less than 1. Stability also captures unstable systems, like the triangle. Remember the triangle? In the triangle, whenever there's, each node can always steal. There's no stable situation here. It's a kind of pathological situation. Okay? So stable outcomes are capturing something nice. They also have limitations. It's not enough. So stable outcomes are not enough by themselves. You might say, yeah, okay, as long as nobody can steal, we're good. But actually that's not good enough, because that's kind of still, it leaves too much freedom. Okay? Here's an example, A, B, C, D. So 1/2, 1/2, 1/2, 1/2. Here's 1/3, 2/3, 2/3, 1/3. Both of these are stable. Okay? Because B and C can do no stealing, because the sum of these two is greater than or equal to 1, which is the other condition from stability. So there is never going to be stealing between B and C because of this. But there's a lot of possibilities. You see? Stable outcomes are too ambiguous. Not allowing stealing is not enough really to fix the values. Okay? There's a large range. Stability is too weak to really determine it. So can we make it better? Yes. So basically the idea is to add the Nash bargaining solution to stability. And that gives us what we call a balanced outcome. A balanced outcome is a stable one, but a little bit more. Each of the matchings is also a Nash bargaining solution. Okay? And here's some examples. So again, I take the 4-node one, because here B and C can steal. Okay, so there's a lot of possible stable solutions. All three of these are stable. And you can see that because the sum of B and C is always greater than or equal to 1. So B and C cannot steal from each other. So all three are stable. But they're not the same. And some of them are better than others. How can we compare them? We can compare them, actually. Notice that I've marked the outside options. Okay? So here, for example, A has an outside option of 0. Of course, there's nobody. Here, since C has 2/3, B would have an outside option of 1/3. If it goes with C, and not changing anything, B would have to accept 1/3. So the outside option for B is 1/3. And the same, the outside option for C is 1/3, and for D is 0. Okay, so we can mark the outside options. You see, the outside option is basically depending on what the other nodes are doing. Huh? If this node is taking 3/4, the outside option will be 1/4 to make a link there. Okay? But now we can check what happens with Nash bargaining. Okay? For example, if you look at the bottom one here, so what is the Nash solution here? Okay? So A is getting a 1/4, but A has outside option of 0, and B has outside option of 1/4. So the surplus, remember the surplus is 3/4. If A gets this and B gets this, there's 3/4 left over, which we divide equally. So A would get 3/8, and B would get 3/8 plus 1/4, which is 5/8. Okay, it's marked here. 5/8 and 3/8. But that's not the same number as here. So this solution is not Nash bargaining solution. Okay? The solutions are not divided. So A is not getting enough. Okay? A is only getting 1/4, but according to the Nash solution, A should get 3/8 here. So A is not getting a fair share. A should be getting half the surplus, but is not getting it. And B is getting too much here. So this is not Nash. If you look at the middle one, the two outside options, 0 and 1/3, the surplus is 2/3. So each one will get 1/3 of it. So A should get 1/3, and B should get 1/3 plus 1/3. And that's exactly what they're getting. So this one is a Nash bargaining solution. A is getting fair share, and B is getting a fair share. He's getting each of half of the surplus. So this one is Nash. And the top one also is not Nash. So you see, if you take all the possible stable solutions, then you pick the one that's a Nash bargaining solution because it splits the money fairly. Okay? What that means, the second example is balanced. Balanced means that all of the matchings are Nash. All of the negotiation is fairly splitting the surplus. Okay? So only the middle one is doing that. The other two are not balanced. This one is unbalanced, and you can also figure out that the top one is unbalanced. I won't figure it out, but you can figure it out. Okay? So you see, stability is a weak thing. It gives you possibilities, but you have to pick the fair one. And there's only one fair one here, which is the one in the middle. And this is the theory of balanced outcomes. A balanced outcome, an outcome is balanced if for each edge in the matching, the money that is split is the Nash bargaining solution for the two nodes, given the best outside options for each node. That means each node, it feels it's getting a fair bargain. Okay? In this example, B and C, the nodes in the middle, the Nash solution means that B and C are happy. They're getting their fair share. Okay, so that's the balanced outcome. Notice, if you want to compute this, notice that this is actually a recursive definition. If you want to compute it on a real network, and I propose that you do some exercises on this, the values of nodes B and C, okay, B and C, depend on their outside options. But these outside options depend on the values for the other nodes. But those other nodes have their own Nash bargaining solution, which depends on their outside option, which goes back to B and C. Okay? So in fact, there are circular dependencies. This is an actual recursive definition. In order to calculate the outside options, you need to know that the outside options will depend also on the values of B and C, okay? So in real life, if you want to calculate this, this actually gives you recursive equations, but you can solve, which can be solved, okay? Any network with a stable outcome also has a balanced outcome. That can be proved. I won't prove it, but you can prove that. And so this is the theory of balanced outcomes. This is how humans are negotiating, it seems, what people think. Of course, there's something which I don't mention. Any extreme, like 0, 1, any extreme solution here will be made softer, of course, because of the ultimatum game. So that means that this is, you have to add the notion of softening the extreme imbalances. So balanced outcomes that are not extreme is how humans negotiate. Maybe, okay? This is actually a question that's not solved yet. This is still kind of research. You see, this is kind of a subtle area to understand this, but it actually comes pretty close, okay, to how humans are thinking. Notice I said any network with a stable outcome also has a balanced outcome. So I have a question for you. Does every network have a stable outcome? What do you think? Does every network have a stable outcome? Actually, I gave the answer, okay? If you pay attention, think. So what do you think? Does anyone know? Is it true that every network has a stable outcome? What do you think? Yes or no? No? No one guess? There's actually a slide with the answer on it. Oh, okay. Well, the answer is no, of course. We saw a network that has no stable outcome. It's the triangle. That's an unstable network. So it's not always possible. So what happens in real life in these unstable networks, it's kind of chaotic. There's no one solution. It actually depends kind of on the time limit of the negotiations, because nodes can always be stealing things, and when the negotiation stops, it's whatever it is, okay? So there's no one stable, no one real solution for such a network. It will not converge. It will kind of keep oscillating. But if there is a stable outcome, then it will also be a balanced one. Remember this one? This is what I call the stem graph. It's a triangle with an extra link attached. This one does have a stable and therefore balanced outcome. We can actually figure it out. C and D will be in equal power. They will exchange half and half, okay? And so this will be half and half. But what does that mean? It means the outside option for B is 1/2. Okay? And the outside option for A is 0. So the Nash solution here, so the surplus is 1/2. 1/2 plus 0, and that gives you 1/2, so there's still 1/2 left over. Divide by 2 is 1/4. So that gives you 1/4 here, 1/2 plus 1/4, 3/4 here. So this is the Nash solution here, okay? This is also the Nash solution here. If you compute, they both have the same outside option, and they have the same numbers. So they're also getting a Nash solution. Okay. This is the theory of balanced outcome prediction for this network. Now, if you put humans in a room, 4 humans, and you let them negotiate, they do come up with something that's similar to this. Okay, in experiments, humans are going similar to that. Okay, it's interesting, huh? So if you're ever negotiating with in a small network with other nodes, it's very important to find out who knows whom, so that you know the topology, and then you can figure out what is your best way of negotiating, okay? And including for this, balanced outcomes, you can compute them. They exist whenever a stable outcome exists, and you can find the balanced outcomes for any network if they exist now. As far as we know, it corresponds to what human beings do when they negotiate. Still a hypothesis though. But this is actually a subject called cooperative game theory. How will players who are kind of collaborating divide up values? Cooperative game theory, so I'm not going to say more about that. Okay, so that's all I want to say about that. Okay, so this kind of summarizes it. Position of the network, the three principles, and the proposed model as the theory of balanced outcomes, which corresponds to how humans negotiate. Okay, now we are going to a next part of the course. We're going to do applications on large networks, and the first part of that will be the web. And before we do that, I want to summarize what we saw and give you kind of a big overview. In the first part of the course, we saw graph theory and game theory. Those are the two pillars. We applied them to human beings. Then we saw markets and negotiations, which is actually already applying both graph and game theory. Yeah? And then in the second part, which is what we're going to see now, we're applying this going to apply to real networks, web, search, information networks, economic networks. Okay, let me give you some principles that are kind of connecting everything together. First of all, in all these complicated situations, they're always converging, moving toward equilibrium, okay? If you have a, remember, structure balance with enemies and friends, this is converging. All the triangles that are kind of unstable are disappearing. It's converging towards, let's say, two groups that are enemies. Or this thing is always converging. If you let the humans talk, eventually it will converge to this kind of a value, okay? Markets are converging, supply equal demand. It's not a static thing, it's converging towards that, okay? And we modeled all these situations by a simplified model, formally defined, precise, and then we show that the intuitions, what they say about the real world. So this gives you powerful tools, actually, okay? So this is kind of a summary of the kind of evolution, convergence. So you have to imagine that real world situations are always dynamic, they're always changing, but they're always moving toward some kind of a stable equilibrium. Okay? For example, and I'll give you now many examples. Triadic closure. Friends of friends become friends. So the network is converging towards a network where everybody is friends. Or structural equilibrium with enemies. Well, the network will be converging towards a group of friends and a group of friends with enemies in between. And you have these unstable triangles. Remember, there was triangles which are kind of unstable. Remember that the one was plus minus triangle. So this one will tend to disappear. If A has two friends and they are mutual enemies, that's not a stable situation. Either these two become friends, or A and B will become enemies, for example, or something will happen. So this system will converge again. And then in game theory, we have the Nash equilibrium, where the players are converging to an equilibrium between them. Each has the best response to the other. That's an equilibrium, okay, between both of them. But it's a local. It's only for the players. But society also likes to converge. Society, and there's different ways, Pareto optimum or a social optimum. Societies will be tending to have agreements that maximize social optimality. So there's some conflict, of course, between these two, and that depends on the society. In auctions, second price, which is the important one, bidders will converge to their true values. If you do auctions over and over, the bidders will tend, even intuitively, will go toward the true values, or market clearing. Okay? Supply equals demand. So the prices will converge so that the sellers can sell and the buyers can buy. Okay? Or trader equilibrium. With it, you have traders, intermediaries. It converges depending on the monopoly or competition. There's always things that change. There's a sound problem here. I have no idea where that static came from, sorry. Try to ignore the static. There's a bad connection somewhere. Touching the metal. Debugging of electronics. Okay. Scratching against the metal. Okay. So convergence. So I converge towards silent auditorium. Negotiation. Remember, we have reducing instability. So if a node wants to cheat, it will cheat. But once it's cheated, it's happy. So the number of nodes that want to cheat goes down because we're evolving towards a situation where all the nodes who want to cheat have actually cheated, unless you have an unstable network, of course, where there's no convergence. And in the balanced outcome, you will converge toward Nash fair division. So you see, there's a principle here through the whole course, that all real systems, networks, like internet, are always evolving towards some kind of a stable thing. So all of the instabilities kind of are disappearing, and this is always going on. So whenever you're studying in real life situation, you have to imagine that, okay? Okay, so I think that is the end of that. That's the end of the first part of the course. So that gives you then an idea also then of how the course is structured. So that's important to understand. So let me now start the second part. Now we're going to be more applying game theory and graph theory to real big networks, things that we know. And the first one that I want to talk about is the World Wide Web. Of course, everybody knows, I don't have to say so much. It's the most important information in an economic network which is overlaid on top of the basic internet structure. It's fully decentralized. There's no single control anywhere. It has an emergent structure, which I'll explain. The whole decentralized state has actually a structure that you can analyze, which emerges. It means that no one organization decided on this. It's a property of the underlying laws of how it's built. Okay? Now we want to search information on the web. It's very big. The problem is abundance. There's too much, billions of pages. How do we get rid of bad and look at the good? The solution comes through link analysis, which is a way of studying how the web pages are connected. And this leads to a basic important algorithm called PageRank. And then I'll talk about Web 2.0, which is evolving. It's not just HTML pages, but there's three principles: content, services, and people, and also targeted advertising, which I mentioned already. How does a paid link get priced? It's through a second price auction, and this is how Google is making all its money. And we will also talk about how to cheat. So if you want to know how link farms work, or search engine optimization, I will explain that too. Okay? So let me talk a little bit about structure first. This is very well known. There is a protocol, a stable decentralized transport network, that's the internet, and there's two basic protocols, IP and TCP. You've already seen this in your networking course, and there's an addressing protocol called DNS, and all other networks are laid on top of that, okay? Facebook, Twitter, and the World Wide Web, which is a hypertext graph, okay? The most important information network on the internet. The World Wide Web is a hypertext graph. Hypertext means that you have a page of text, and on that page you have links to other pages. So instead of a book where the pages are sequential, the pages are organized as a graph. So that's hypertext. Hypertext means the pages are not organized as in a book sequentially, but arbitrarily as a graph. So that's hypertext. And you can go from one page to the other by following the link. And the other principle is network distribution. The pages are geographically distributed all over the internet. So this hypertext graph is completely decentralized. This idea was originally developed, so hypertext is an old idea, but the connection of these two was originally developed in the 1989-1991 at CERN by Tim Berners-Lee and Robert Caillot. And both of these guys got ennobled. So Tim Berners-Lee is now known as Sir Tim Berners-Lee, and Robert Caillot has the Ordre de Leopold, something or other. So this guy is actually in Belgium, and it's widely forgotten that this was not only developed by this Englishman, Tim Berners-Lee. Okay? And it's a European invention, not American. So the key feature is that anybody can publish documents, and you have also access to documents. So everybody is both publisher and consumer. It's completely decentralized. Anyone can contribute. And it is defined by a protocol called HTTP, which is overlaid on top of TCP. Okay? So I'm not going to talk about the details of HTTP. We're going to talk about what happens above that. Okay? It's actually quite interesting to look at the history of the internet, especially if you want to be innovative. There you have to look at what goes on in the past. So the web was not invented from nothing. There are many interesting precursors. This is a typical precursor, very important. This is citations of scientific publications. Okay, each scientific work has a bibliography citing other works. So you can consider it as a hypergraph of papers. Okay, so the Granovetter paper references the Travers-Milgram paper of '69, which references the Rappaport paper from 1953, for example. This is actually mostly directed acyclic graph because citations are always going into the past. So the difference between this and the web is that in the web you can have cycles, of course, but here it's always going into the past. Almost always. There are a few exceptions. Two papers published at the same time can reference each other, right? Also, this is a fixed graph, which is always growing, whereas the web is not fixed, but is actually changing. Pages can disappear or change. Okay? And this kind of a graph has existed already for a long, long time. That's one example. Another example is encyclopedias. So an encyclopedia is a very big book that tries to summarize knowledge. Okay? Wikipedia is interesting because it's an encyclopedia built on top of the web, but this also is true for encyclopedias, book form encyclopedias. So encyclopedias have articles, but they reference other articles. Okay? And here's some examples. So here in the middle there you have John Forbes Nash. So this is the mathematician who came up with the Nash equilibrium. So you have an article on him, you have an article on Nash equilibrium. There was a movie made about his life called The Beautiful Mind. Okay, this John Forbes Nash was also working for RAND Corporation, which is a big think tank doing highly technical stuff in the US government. RAND Corporation, of course, is referenced by many conspiracy theories, and also NASA is a subject of conspiracy theories. NASA, of course, is connected to Apollo 13. There was a movie, Apollo 13. This movie was directed by Ron Howard, who is also the same guy who directed Beautiful Mind. So you see, there's a lot of recursiveness in it. This is called associative memory. So when you look up information, you don't look up the information from the name, from the address. You look it up according to the content. You say, I want all information on conspiracy theories, and in any article talking about conspiracy theories, you will get it. This is called associative memory, okay, where you can actually look up information because of the content. Okay, this is related also to something called a semantic network, where the nodes are concepts and the edges are relationships between concepts. It's not exactly the same, but conspiracy theory is a kind of concept, okay? And NASA is an organization. It's an example of an organization. So it's not exactly the same, but there is a close connection to this, okay? So encyclopedia is kind of precursor to this. And now I want to mention two very interesting people who actually imagined the web a long, long time ago. The first person is Vannevar Bush. He wrote an article, it's on the Moodle, by the way, called As You May Think, which appeared in a magazine in 1935. So he was a scientist. He was actually the National Science Advisor in the United States government up to World War II, and so he worked also on electronic computation and stuff. But he imagined something he called a memics, device, all human knowledge digitized, connected by associative links. That means you can follow the content. In those days, nothing really existed like that, okay? This is foreshadowing a lot of the web. If you look at his article, you should read the article. It's very interesting to see how he thinks in 1945. The human mind operates by association, okay? A memex is a device in which an individual stores all his books, records, and communications, and which is mechanized so that it may be consulted with exceeding speed and flexibility. Okay? And he has pictures, and you can have you see the picture in the article where you have a desk with all the devices, okay? So that's one very interesting thing. But Vannevar Bush is not the first person to imagine the web. As far as I know, the first person is a guy named Paul Auclair. This guy was a documentalist. He was an entrepreneur. He made large organizations. He actually made a physical form of the internet using libraries and the nodes and telegraph connections as the network in the 1910s and 20s. And there was actually a search engine. You could send your search queries, and the libraries would communicate to each other through the telegraph if they didn't have the information to get it, and then you would get a reply back. So it was kind of a slow form of search on the internet in like the 1920s. Okay? His vision was what he called a universal book. So Bush talked about memex. Here's universal book. And he was an idealist. So in the days before World War II, people were motivated by stopping wars. And the idea was that if you educate people and bring all the information, organize it all together, that will promote world peace. Okay? Okay, so you can, I don't know how far that can be pushed, but it's a very nice ideal. So his vision was the universal book in a collaborative network, accessible in the homes through a network. Okay? Achieving peace through universal dissemination of knowledge. This was kind of a 19th century utopian vision, but a lot of people believed in this. Okay? So if you, also in the middle there is some documents. So his traité de documentation, so his documentation treatise, the book on the book from 1934, what I will translate here, the universal book consists of all books, and it's like an extension of your brain. The workspace has no book. There is a screen and a telephone. Far away in a huge building, all the books and all the information are there with all the cataloging, bibliographies, and index. Okay? You can access it at a distance with or wireless or wired by television or teletography. I guess that's writing in a distance. So then you have what appears on the screen is the page you want to read to get the answer to the questions that you have posed by phone or wireless. The screen could be double, quadruple, or tentuple, many screens. So he had already imagined computers with many screens. If you want to multiply text and documents and see them simultaneously, there will also be a speaker if you want to aid vision by hearing. So he also imagined multimedia, okay? Okay, this was written in 1934, and he tried to implement this with the technology of his day. He actually was one of the pioneers of microfilm, which was an early form of data storage, and he made a networked connection of libraries connected by telegraph, which was kind of a steampunk version of the internet, if you want. This was all in the 1920s and 30s. Okay? Unfortunately, most of all the documents he collected were destroyed by the Nazis during the Second World War. That's kind of a tragedy, because he collected millions of documents. Okay? So this is interesting, huh? You can see that these ideas are not coming out of nowhere. People imagine it way in advance. Huh? So Bush and Roubaix are the kind of visionary people. So it's very important that you can see how they think. How did he imagine it? He basically took an idea and pushed it to the limit. I have a book. I want a universal book. What does that mean? Okay, he took something that he had and he basically pushed it to the limit. And then he imagines what that could mean. Okay? Okay, let me make now a small break, and then we will look back on the web. Now we'll talk about the web. Let me first talk about the structure as a graph. The web. The web is a directed graph. Information networks are usually directed because you have a source and something you're looking for. Social networks are usually undirected. Global friendship is undirected. A and B know each other. But sometimes it's directed. A has heard of B, for example. And some technical knowledge, a path from A to B is a sequence of nodes that starts with A and ends with B, which is already. And a directed graph is strongly connected if there's a path from every node to every other node. Okay? A strongly connected component. Okay? So many graphs are not strongly connected, but you have to understand how to navigate. You can partition the nodes into connected components in the same connected component with each other, so it's symmetric. But in a directed graph, it's not so simple. And what you do is you define the notion of a strongly connected component, SCC. In French, un composant fortement connexe, CFC, SCC. So this is a standard term. And there's two conditions. Every node in this subset has a path to every other node, and the subset is maximal. That means you cannot add more nodes from the graph and keep the same property. Okay? So it's a maximal subset that has that property. And you can take the directed graph and turn it into an acyclic. All the cycles are actually inside the strongly connected components. Okay? And each strongly connected component is like a supernode. You can turn the original graph into a graph of supernodes. So here's an example. This is a kind of a web, part of the web. Universities, classes, blogs, blah, blah, blah. Directed graph. But there's some cycles here. So for example, you have University of X, classes, networks, class blog, blog post, rankings, featured column, go back to university. So all of those nodes are a strongly connected component. So you can turn that into a single supernode here. So this is a supernode. This little piece is also a supernode, strongly connected component. Right here, this is another supernode. And this little node is also a supernode by itself, because there's no other nodes there. And if you look at how the supernodes are connected, there's no cycles. It's acyclic. There's no cycles, of course, because if it would be a cycle, that would be another strongly connected component, okay? You can therefore turn any graph into a graph, an acyclic graph of the strongly connected components, okay? And so we can do that to the web. It turns out in the web, there is it's a bow tie. There is a single very large strongly connected component. So this I explained already in the very first lecture. Then there's all the links going towards that, and all the links coming out, but not coming back. Okay. Then you also have tendrils and tubes. Tendrils, debris, if you want in French, are paths coming out from the in, but not going anywhere, or they go into the out part, so they're not part of the strongly connected component. You also have tubes directly connecting the in to the out nodes, so it's a kind of very weird animal organic structure. You also have pieces that are not connected to anybody, small versions, and the approximate size, so 17 million nodes is connected. Most of those, so more than a quarter are here, 44 million here. This is about the same size. The tendrils and the tubes are also about 44 million, okay? This structure is always true. This has been first found in 1999 or something, okay, when there was still already a couple hundred million, 200 million nodes in there. So this looks like a bow tie, a nœud de papillon in French, huh? Okay, another thing is Web 2.0. In the original web, it was pure hypertext. Pages with links, pages with links. Pages were static and new pages were always being added or changed. But this has changed. This is during the first decade, 2000, 2009, the level of abstraction of the web increased. It's not anymore the pages. The pages is like machine language, if you want. The linking of the pages is still there, HTTP, but it's not the thing anymore. It's like the compiled binary. It's like the machine language. Now, the web is managing content. Content is not just one page. It's a whole subgraph. For example, I have a website of all the stuff that my group is doing, or the university has their site. This is a lot of content, but it's not just one page. And when I manage it, I'm not managing pages, I'm managing the whole thing. So in my point of view, I'm managing content, and then it's compiled down into pages. Okay. Also, there are services now. A service is a piece of software that does that. For example, blogs software, or database software, or Facebook software that manages your wall and your homepage stuff from Facebook. It's services. So you have all these little programs that are working to manage subsets of pages. Services, and not people, sets of pages. And the actual connections, the links between the pages, that's the machine language level. The actual connections are between people. My Facebook page or thing is connected to my Facebook friends. And of course, there's a lot of links in the pages, but conceptually, it's a link between the two owners, the two people. Okay? And that happens for all of the social networks. So you see the abstraction level has increased, and the links between pages is just a kind of machine language. 3 examples. Wikipedia is shared content. So that's principle 1. Gmail, or other kind of online mail, it's managed on web pages, okay? It's a service, that's 2. Okay, connections between people, I mentioned Facebook. There used to be a thing called MySpace, which disappeared, I guess. Maybe it still exists, I don't know. It was a competitor to Facebook, but Mark Zuckerberg got very hungry and he ate MySpace. Okay? And you can see phenomena. In this course, we're studying large-scale network things that happen. And 3 examples in the web. Software that gets better the more people that use it. This is something we'll see in the course. Things are better when many people use them. The typical example would be, in the olden days, was fax machines, if you know what they are. I used to use that. But it could be anything. It could be PDF or Word documents. It's useful because everybody has Word, okay? It's useful when more people use it. Online services are more useful as more people use them. eBay is more useful as more people put objects for sale. The more objects there are in eBay, the more interesting it gets. This is called a direct benefit cascade. And we will see it in the course. We're going to study that principle. This is a big network effect, okay? Another thing is called the wisdom of crowds. If you have many people working together in a smart way, they can be much better than just one person. Wikipedia has collaborative authorship, and the experts are correcting each other's mistakes. That means the quality is very good, okay? Breaking news, news content on Dig, which maybe still exists, I don't know. But it might fail. This is not always true. Sometimes crowds are smarter, but sometimes they are more stupid. And this is called network cascades. So we'll see that also in the course, okay? A third thing is the long tail. La longue traîne in French. A huge amount of less popular content. It's not enough to sell popular books. You also have to sell unpopular books. The reason why supermarkets are good is because they have an enormous number of different things. Most of those things are not so popular. So you have a huge amount of less popular content. So it's like a tail end. So very popular and then less and less, but it's very, very, very long. This less popular content, if you combine it together, it's often bigger than the popular content. So Amazon has millions of items for sale, but most of those are very unpopular. Almost nobody buys them. But all together, they are extremely popular, and it's the reason why people go to Amazon, because of all that unpopular stuff. This is called the long tail, and it's a reason why internet software is sometimes incredibly successful, and there's some mathematical laws connected to that, power laws, and rich get richer, which we will see later also in the course. Okay, so these are social phenomena that happen on networks, and we can understand them using graph theory and game theory and sociology. Okay, okay, good. Now let me go on. Now let's look at search. The problem of search. You want to find information, of course. So the web is only useful if you can find what you want. This is called information retrieval. And the classic way of doing it is with keyword queries. The keyword queries. But that's not very smart, but people try to make it smart. Okay, so you have indexes in books. You can search for words in files, but it's usually keyword. Even Google search is using keywords, but keywords is what's usually used, even though it has problems. It's not so expressive. You cannot express subtle ideas using keyword combinations. So if you want to express a subtle concept from philosophy and you want to find works explaining that, you don't have an easy way of doing it. It also has what's called synonymy. Same words, multiple words for the same concept. In English you have scallions, which are green onions, synonyms. Or also you have polysemy. This is the same word with multiple meanings. Well, if I look at a jaguar, it could be an animal, but it could be a car. Okay? That's probably the part of information retrieval. This was the old problem. But now there's the new problem with the web. The new problem, decentralization. Everybody is an author. It's not just one publisher organizing very nicely the stuff. No, everybody all over the place is creating documents. It's a mess. How do you organize all that? Everyone is an author, and everyone is a searcher. That means nobody can, how do you control that? How do you search all that? Also, the quantity is enormous. It's huge, billions of pages. Also, it's always changing. It's always changing. Now, if you went on September 11, 2001, which you recognize, I think, yeah? If you type World Trade Center in Google on this day, you did not get images of the terrorist attack because Google is not that fast, okay? But the building, which was still standing in the photos, but even though it was collapsed. So the information is changing, so you have to update. And it's always changing. You have lots of real-world information. You have these problems, okay? You have to track the changing information. It's huge. And it's a mess. Everybody is creating information everywhere, okay? Also, there is too much relevant information. If I want to look about, for example, radar technology, how does it work? There's millions of pages that mention radar. Which is the right one? There's too much relevant information. Too much. Abundance. Search is not scarcity, it's abundance. The problem is there's too much. So how do you solve that? How do we find the right page? Okay, so we gave a one-word search, Cornell. Cornell. There's actually a university called Cornell University, and that's what I'm interested in. But also, there's also people who are called Cornell, but I don't care about them. I want the university. How do I get to Cornell University's homepage? Okay, well, we want to build the algorithm. Okay? The page itself will not help. Okay? Many pages discuss Cornell University. There's nothing on the page. The only reason Cornell University's homepage is special is because other pages are linking to it. Okay? So the point is the graph structure is going to help. Okay? We gather any page that is somehow relevant to Cornell, and we see what those pages are pointing to. So if we find the page that has the most inlinks coming from these relevant pages. Okay? But still that's not good enough, but let's see how we do it. So let me show you an example. Okay, I want newspapers. This is very American, Silicon Valley centric, you will see. Okay? We count inlinks. I want newspapers. What I want the best newspapers. I type newspapers. Okay? All these little ovals are pages that are somehow relevant, that somehow talk about newspapers. And they will have links. Okay? And we look at the pages they are pointing to. So this one, Amazon gets 3 links. USA Today, which is a newspaper, also gets 3. New York Times gets 4. The top one, San Jose Mercury News, gets 2. Okay? So Wall Street Journal and New York Times get some votes. USA Today gets votes. But Amazon and Yahoo get also votes, but they're not newspapers. Why? Because they're just so popular that they just show up. Okay. So it's not enough. So this is not enough. This will not find us the best newspapers. You see, this is like the first step. Huh? I start from all the pages that somehow mention newspapers, and I look see what they're pointing to. Okay? But still, it's not good enough. Okay? But now, let's look at the other directions. The idea is to try to improve this approach. Try to find an algorithm that will help us. Some pages have lists of newspapers. Okay? A list is a page that has a list of resources. For example, here are some good links, and then here are some nice newspapers. Okay? Okay? How can we find the good lists? Okay? Well, look at the pages with the highest number of votes, and who is linking to them? Okay? So this one with the 11 is pointing to San Jose Mercury News, Wall Street Journal, New York Times, and USA Today. And we give it votes. We add the number of links from each of the destinations. So that one will get 11. 2 plus 2 plus 4 plus 3. Because it's pointing to 4 guys who have 11 votes. This one will get 7 votes. This one will get 6. It's pointing to Amazon and Yahoo. Okay? So this gives us already a kind of ranking. This 11 one seems to be pretty good. So you see what we're doing? We're kind of following the structure of the network. And we're doing it in 2 directions. We're doing it where you're linking to, but also where it's coming from. Okay? Okay. You see, we started by having votes on the right, and then we add them up on the left. Okay? But now we can iterate. We can take a look at New York Times and add up all the numbers of the ones that are pointing to it. Okay? So that will change the score. It goes to 31 from 4 votes. So you see, we're going back and forth. See, we want to somehow focus on the good ones. So it starts here. All the pages that are talking about newspapers, we see who they're pointing to. That gives us a number. And then we go the next step. The next step is the ones that are pointing. We add up what are the votes where they're pointing to. So you see, somehow the good ones are going to start emerging from this. The third step is you add up the ones on the right, you add up the points from the nodes on the left. New York Times will have 8 plus 11 plus 7 plus 5, okay, which is 31. So we repeated improvements. And each time we improve, we will somehow, the real newspapers will emerge from this, okay? That's kind of the magic of this approach. Now, the numbers are always increasing, so we normalize them, okay? All the pages we point to, we divide by the sum so that it's all turns up to 1. We divide by the sum of all the page scores, because otherwise the numbers keep getting bigger. So you can see that they're normalized here. Here, New York Times is 0.248. Facebook is a little bit less. And you keep going. And you also normalize the ones, these. And actually, this will achieve a fixed point. This will go to a final result. Okay? This is called hubs and authorities, this algorithm. Hubs and authorities. These guys are the authorities, the newspapers. They are the more authorities. The hubs are the ones pointing to newspapers. Okay? The French version is kind of strange. Authorities is autorité. Hubs is called concentrateur. Okay. Somehow it concentrates good links. Okay. Hub is, I don't know, maybe it's harder to translate. But you can actually keep track of these scores. They're like two vectors. The authority of a page, this is a number, and the hub page gives a number. So the algorithm I just showed you, you keep iterating until you have that fixed point. You go back and forth, you keep normalizing, and eventually these numbers actually will converge. It's a fixed point. They will converge. Okay? This gives you an algorithm. You start with all hub and authority equal to 1, and then you repeat. Of course, you start by the set of pages that are relevant. Okay? If you want to do newspapers, first of all, you look for all the pages that actually mention newspapers. And then for all those pages, you start with hub and authority equal to 1. And then for each page, you update the authority to be the sum of all the hub pages pointing to it. And then for each hub is the sum of all authority pages it points to. And each iteration you normalize again so that the sum of those is always equal to 1. You see? So somehow a page is important if a lot of important pages point to it. And a page is important if it points to a lot of important pages. That's kind of the notion of importance. And those are recursive definitions. So to find the really important ones, you have to iterate until it converges. And then you find the pages that are important because the important ones are pointing to it, okay? And the pages are also important because they point to important pages. And this actually converges. I'm not going to prove that today, but I will prove that next lecture when I present another way to show this algorithm. The limiting values are independent of these initial values. One, it's based completely on the structure of the network. It's interesting, huh? So here is a pseudocode algorithm. So authority and hub are like vectors, huh? So for all the pages, you set them equal to 1, and then you have an update step. For each page, the authority of the page is the sum of the hub of P prime, where P prime links to P. Okay? And the hub is then updated to the sum of all the authority of P prime, where P points to P prime. You see, these are the kind of update steps. And then you have a normalization step. You take authorization, authority is equal to authority divided by the sum of all authorities. So this makes it, so the sum is always 1, huh? And you do the same for the hub. And if you do that over and over, eventually it will converge. And for our example, the limiting values are here. Okay? So it's funny, you can see New York Times has a high score of 0.304, whereas Amazon has a low score. Actually, New York Times has a high score because many pages that are important, that are relevant to newspapers, point to New York Times. Okay? And they are important. Why are they important? Because they point to important newspapers. So somehow, the newspaper, the actual newspapers have come up out of the chaos, this information, out of this huge graph. We've somehow isolated this information. It's kind of like magic, yeah? Well, this magic is why Larry Page and Sergey Brin are multi-billionaires today, okay? They understood this in 1990. Okay? So PageRank is actually even a simpler algorithm than this. So you see how we did it, huh? With the hub and authority. Actually, you don't need hub and authority. Only one number. It's enough to have only one number. Okay? And And this leads to a page, the algorithm called PageRank. And this is what the foundation of all the power of Google comes from this algorithm. You see, algorithms can be very powerful things, okay? And I remember this time, the early 1990s, the beginning of the web. The first time I used the web was in 1990. When did you use the web the first time? I don't know. 1990. In those days, many search engines were trying to organize information. All of them, almost all of them are forgotten today. Alta Vista, Lycos, WebCrawler, Yahoo. Yahoo still exists because they're not just web page, they're also doing other things. And they changed their search engine. It was Ask Jeeves. And then Google came along and destroyed all of them, okay? Because of PageRank. Because it was immensely, much better. And in those days, they were very, very arrogant, or maybe they still are. They had this one button on their page, they think, saying, I'm feeling lucky, okay? If you click there, you only get one link. And they were so confident that this was the right link for you, okay? So PageRank is actually an improvement on Hub and Authority. It only uses one value, the importance of a page, and that's actually enough. If a page is important, it will also be, it'll be both a hub and an authority, okay? It means that if New York Times is important, that means it's also important as a hub. All the links coming out of New York Times are usually pretty good, okay? Because the New York Times is not going to put crappy links on its site, okay? Only good links. So, PageRank, they were correct. Only one value is needed. Important pages are pointed to by important pages, and important pages point to important pages. So again, this is recursive. And so, PageRank is an iterative algorithm that goes to fixed point, and it has a really nice intuition. So maybe you have seen already in another course, PageRank, right? Which course was that? You saw it as eigenvalue problem, right? Okay, did you see the intuition of it? Do you really understand why it works? Or they just present to you some simple mathematical equation and say, look how trivial it is. Yeah, it's a random walk. Look, it's so simple. Us mathematicians, we understand it so well. It's so simple. But those mathematicians saying that are not billionaires. Okay? Okay, so I'm going to try to, so you're going to see PageRank again in this course, my way. So you will hope in different approaches, not just the random walk or matrix, but also a very good intuition approach and the connection to information retrieval. Okay. Also, you're going to see link farms. Did you see link farms in this other course? You're going to see how you cheat with PageRank. So I will tell you that too. Okay. So here is how the intuition of PageRank. There is a fluid. Each page is a container with liquid. There's 1 liter in there. And the links are pipes. Okay, the amount of fluid is constant, so automatic normalization. Initially, each page has 1/n of the amount of fluid in it. And in each iteration, you spread the fluid over all outgoing links, and the same amount goes, it's divided evenly. Okay? A page has m outgoing links, so there's the PageRank on the link. So the fluid on the page, divided by the outgoing links, it goes onto the link. And then the new fluid is the fluid coming in. So all the fluid goes onto the pipes. So the page is empty. And then all the incoming links collect all the incoming fluid. Okay? That is exactly the intuition. And that's exactly how it works. And you can do computation. And since you are all very smart mathematicians, I don't have to show you, right? Or do I have to show you? Do I have to show you? I'll show you a little bit. Here's an example of a network with 8 links. Initially, all pages get 1/8 of the fluid. And in each iteration, so here's iterations, they will converge. And you can work it out. So for example, H, all the fluid goes out here. The fluid comes in from D and E. But D spreads its fluid in 2 pieces. So 1/16 comes down here. And E spreads its outgoing in 2. So 1/16. So it's 1/16 plus 1/16 is 1/8. But if you look at A has the D, which is 1/16, plus the E, which is 1/16, plus the H, which is 1/8, because there's only one outgoing link, plus F, which is 1/8, plus G, which is 1/8. So A will be 1/2. Okay? And then you keep going until you get fixed points. So the equilibrium, or fixed point, is this. Okay? So A will be 4/13, B is 2/13, 2/13, and all the others are 1/13. Okay? That you can compute. Okay? Of course, this definition has a problem. This problem was first recognized by Larry Page and Sergey Brin. I always wonder if the name of Larry Page has something to do with PageRank. I'm not sure. Okay. There's a problem with this basic definition. Let's say I have this graph here. What happens here? What happens in this graph with my fluid definition? Okay. F and G are now pointing to each other and to nobody else. Well, any fluid that comes into C will never go out. Okay? So eventually, all the fluid is going to collect here. Okay? All the PageRank fluid will end up in F and G. They will each have 1/2. Everyone else is 0. So it looks completely bad, huh? Did you see that problem in your math course? Yes? No? Maybe? Who is this non-intuitive professor who showed you this algorithm? Who is the guy? Give me his name. I will challenge him to a duel. Okay, so what do you do? So it seems completely bogus, huh? You see, I don't mind formulas. And next lecture you will see the eigenvalue and definition, and I will even give you some very nice, show you nicely. But you have to start with the intuition, okay? So I would be a very bad collaborator for Louvain, very, very bad. So how do we fix this problem? This is a big problem for PageRank, okay? It doesn't work. Yeah?
On ne peut pas juste considérer que s'il y a un lien bidirectionnel entre 2 jeux, il n'y a pas de lien du tout. Parce que si moi je réfère une page, je ne peux pas me référer à moi.
Oui, mais si tu enlèves ça, so the idea question is just avoid all bidirectional links. Well, clear. If you remove this two purple links, what's going to happen? Well, you need some outgoing links. Assume F is pointing to itself, G is pointing to itself, okay? Again, all the incoming fluid will never go out. It will still all collect here. Huh? So it's not because of the bidirectional link, the problem, huh? I mean, it could be a bigger cycle or something. This part also has cycles there. It's not the fact that you have a cycle is a problem. It's the fact that you somehow partition this graph. That the whole graph is not a single structured, strongly connected component. That's the problem. And you cannot guarantee that. Because in the web, everyone does what they want. You cannot guarantee this kind of structure. Okay? So the fix. This was actually a very genius idea from the two guys who invented Google. You can fix it using the fluid intuition. And it fixes by thinking carefully. Look at the water on the earth. Why does it not all flow downward and collect at the lowest points in the oceans and the lakes and never go up. Because there's another process which makes water go back up, which is evaporation. So the water actually cycles. And we can exactly model that in a very nice way in PageRank. This is called the scaling rule. The scaling rule is the following. You take the PageRank of a page, you multiply it by a scaling factor. So this is a number between 0 and 1, so less than 1, okay? And the leftover PageRank is spread uniformly over all the nodes. So 1 minus s divided by n pages. So the PageRank 1 over 1 minus s PageRank evaporates from each node and rains on all the nodes, but uniformly, okay? And this completes the cycle. And with this idea, the algorithm is completely useful, okay? The final definition of PageRank has the basic update extended with the scaling rule. And this converges to a unique limit. That's not so hard if you use a matrix representation, which we will do next time. It's an eigenvalue computation. This is actually the definition of PageRank that was used originally, and the scaling factor is between 0.8 and 0.9. That means most of the time you follow the link, but sometimes you're evaporated. Okay? And another way of seeing this, which was mentioned, is you can see this, that it's equivalent to a random walk formulation. Okay? And this also has an intuition, the random walk. You start by picking a page at random. Every page has equal probability. You follow links for k steps. Okay? And in each step you follow a random link. Okay? But at each step, you follow the link with probability s, and you jump to a random page with probability 1 minus s. So basically, it's a kind of a random walk of a certain length until you jump. Boom. So after a certain number of steps, you will jump. You mostly follow the link and sometimes jump. That kind of models how people browse the web, okay? This actually is a very good intuition also. It actually is a good intuition to keep in your head, together with the fluid intuition, which is also a good one. Okay? Okay, so that's all I want to say right now. I will come back to PageRank after the Easter vacation, but let me finish with a little bit on modern web search. Is I have the time? Yes, I think I do. Okay. So in the 1990s, this was central, this algorithm, and it actually is extended by what's called the anchor text. So the text inside the link that you click on, of course, is important. Okay, this describes the target page. Also, the user behavior is monitored. So you tweak the algorithm. If the user uses the second result all the time, the algorithm was switched it. This was the original PageRank. But modern search engines don't do this anymore. It's become a much, much harder problem. And there's basically two reasons. One is cheating. Gaming the system, cheating the PageRank. It has a much better name than that. It's called search engine optimization. It seems very nice, you know, SEO. And there are companies. You pay them money, and your website will increase in rank. Okay, and the more you pay them, the higher it will increase, supposedly. Okay, and you can. There's a nice phrase: web search is information retrieval where the documents are actively behaving badly. So the documents are nasty things. They're filing and they're trying to get up. And the way to do this is called link farms. So I will explain how the link farms work in the next lecture. if you want to build your own. But of course, Google was not stupid. They see this, and they have things that are trying to go against. So it's like a fight between these SEO guys and between Google. And the second thing that changes, which we saw already, is advertising. Okay? Google makes a lot of money with paid sponsored links. And how do you determine the prices? Well, it uses a generalized second price auction for that. Because there's no way you can find out, guess what it is. But the second price auction forces the advertisers, the companies that want to advertise, to put in how much it's worth for them, their true value, okay? And so this has made things much, much more complicated. So my prediction is, because of these two, we are going to reach a singularity. But you know there's this notion called the singularity, if you ever heard of that? When AIs become very smart. That's not the singularity I'm talking about. I'm talking about another singularity. My singularity is, when you click on a web page, the computers will be doing more and more work for less and less result. Eventually they will be doing an infinite amount of work for zero result. When you click on a newspaper page, hundreds of auctions are taking place. Incredible complex techniques of search engine optimization are taking place. And Google's very smart battling that is taking place. An enormous amount of computation is taking place when you click in order to see one page. Okay? It's incredible how much computation it takes nowadays to show just one page. Okay? So that is actually a kind of singularity, an infinite amount of computation for no results, or almost none. Okay? Okay, let me, there's a few other things, but let me stop for today and let me give you a quick summary. So we go back to this. So the web was invented around 1990, decentralized, emergent bow tie, and today we have Web 2.0. Actually, you can hear people talking about Web 3.0, but actually that's still kind of bogus idea. Web 3.0 is supposedly Web 2.0 plus AI and blockchain, but nobody really knows how it's supposed to work. Okay? So I'm not going to talk about Web 3.0. But Web 2.0 is a lot. Web search solves the abundance problem and has made Google very rich. It also has evolved into a whole ecosystem. So there are search engines and companies are always fighting each other for ranking, and advertising is big business now, okay? And so search is a huge industry nowadays. So this very nice, simple web idea has turned into a massive industry. It still sort of works, actually, but sometimes the loading is slow. Okay, let me stop there today. So wait, a few words on the project and instrumentation. So the next lecture will be in 3 weeks. You will get the project. It's a very nice project. In the next day or two. Okay, and you don't have to work on it during Easter vacation because you will have plenty of time after. But of course, you're free, and students like to have the extra degree of freedom. Okay? I will do my best to grade the midterm during the Easter vacation. You can see that professors also have to work during Easter vacation. Okay, so let me stop here, and I wish you a very good Easter vacation.